On number 6, we have a 1-liter solution, which means all our moles turn into molarities. We have a weak acid, which is going to maybe give off some H+. And the reason the HCl does not appear on the left side is that it's a strong acid and all the H's come off when it hits water. So I don't need to discuss how much is going to come off. All of them are going to come off. And that gives me a starting point of H+. That molarity is the H+ molarity. Then what might happen to some extent, but not a full extent, is the weak acid donating H+ and the anion here. So it will donate some amount. It will get destroyed, so to speak, to some amount, X amount, and create one of these and one of those. And then we have these values for equilibrium. Here's our products over reactions to the power of the number in front, but with a Ka, 3 decimals or more smaller than the molarities being discussed. Let's just cross out plus X and minus X. And then we can solve for X. And then the math is pretty standard, just like our previous problems. They do point out that what we just said that is with a molarity like this of H+, adding the weak acid doesn't even really affect the pH. And again, this is a logarithmic scale. Every pH number is 10 times more concentrated, 10 times stronger. It represents 10 times more H+ in water than the last number. The numbers get different from each other by quite a lot. And in fact, we go so small with H+ that this is actually considered a fairly big figure right here. So that's quite a strong acid situation. And I wouldn't put that in my eye. And the addition of this doesn't really end up mattering. Number 7 kind of steps things up one more little bit. And what we have here is a weak acid and its conjugate base. Remember that the sodium will all come off because that's super soluble. So once this hits water, all the sodiums come off. And what we have is just the acetate ion, which is the conjugate base of the acetic acid. Maybe hit pause and have a think there. This is the acid. This is the base that could create the acid if it took another H+ unto itself. So that is a buffer, which is gonna come up. So get started on this idea. A buffer is a weak acid and the conjugate base, or the other way around, a weak base and the conjugate acid. Often used this way though. So it's a 1-liter solution. So again, the moles just become molarities. So I start off with this molarity and this molarity. This dissociates to some amount, destroying some amount and making equal amounts of these. That gives me products over reactants to the power of the number in front. But once again, with a Ka like this and these molarities, I'm going to be able to do that and solve for X. And X is the H+ amount. And then I can do all my previous type math and find all these things. Now, if I just wanted pH, because a lot of times the question just wants pH, I can use another method. And there is a famous equation called the Henderson-Hasselbalch equation, and it will be in the booklet, and it almost certainly will come up to the point where I really recommend memorizing this at least by the end of the course. You sort of derive it. I don't really care. Here's the Henderson-Hasselbalch equation in its sort of standard form. Here it is if you want to find POH. And what this says is pH equals the pKa. Now, I know we haven't discussed pKa, but in the same way that pH is negative log of the H+ concentration, pKa is negative log of the Ka. So this sounds a bit weird, but I say that a P number is the negative log of whatever you're talking about, of the thing under discussion. So pH is negative log of H+, POH is negative log of OH minus, molarities of course, and pKa is negative log of Ka, pKb is negative log of Kb. So this then is the molarity, brackets means molarity, of the A minus the anion, whatever it is, over the molarity of the acidic form of that. And then we take the log of that fraction and add it onto here, and we can find pH. It also allows us to solve for, of course, any one of these things in here, really. But if I wanted to do pH, what I could do then is say, okay, pKa is negative log of the Ka, which I know. And I could say, and then the last part is the log of 0.05 over 0.1, because remember we crossed out plus x and minus x. So let's cross them out. We said they were insignificant, so let's just disregard them. And then we can use our calculator, and we can find this, take log of that, and then find negative log of this, and then add them together, and we get these should be the same pH. There we go.